basically we were talking about how a polynomial can be written in terms of its own derivatives. Very strange notion, but we're just basically saying that this a here can be written as f of 0, and b can be written as f prime of 0. You know what you're looking at right now? You're just looking at basically y equals y1 plus mx. You're looking at y equals mx plus b right now. Y equals b plus mx is what you're looking at. Okay? Obviously, this polynomial is not a straight line. I mean, it's ax squared plus bx plus cx, or a plus bx plus cx squared, etc. So there's a lot of terms, so we have to keep writing if we want more accuracy. So the next term would be f double prime at 0 over 2 factorial x squared, followed by f triple prime at 0 over 3 factorial x cubed. And this just goes on forever.
This was Friday.
This was Friday. And it was posted 3 p.m. video. Okay? So anyway, we assumed also then that sine x would behave in like manner. Okay? So even though sine x isn't really a polynomial, maybe we could think of it as a polynomial and we could figure out its coefficients. So this is a huge logic jump. But what we did was we said maybe it is a power series whose nth coefficient is related to its nth derivative, the same way the polynomial was. Okay? So we assume that sine x would be the same thing as sine 0 plus the derivative of sine at 0 times x to the first, plus the second derivative of sine at 0 over 2 factorial x squared, plus the third derivative of sine x at 0 over 3 factorial x cubed. We just made this assumption, and we found that since the derivatives of sine x at 0 are cos 0, negative sine 0, negative cosine 0, etc. Let's fill these in. Negative cos 0, sine 0, etc. We just get coefficients like 1 and 0 and negative 1 and 0 and positive 1, etc. And this is all starting with the n equals first term. Okay, so then we put these in. So this is actually, just so you know, the first term in our series expansions are always n equals 0 terms for this classroom. So this is n equals 0 term. The 1, 0, negative 1, 0, 1, 0, negative 1, 0 pattern starts right at n equals 1. So you can see it here. Here's the 1, 0, negative 1, 0, positive 1, 0, and so forth. It starts on the second term, actually. In other words, sine x can be written as x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Interesting pattern. And all the even terms just sort of vanish out, and we're left with a series we can write in sigma form that looks like this. There's an odd power of x on top and a same odd factorial on the bottom. It does alternate, so we need a negative 1 to the n there. And we even graphed the first few partial sums. They were just polynomials to see how much they look like a sine wave. And then finally we proved, using the ratio test actually, that this converges for all x. So in other words, our assumptions must be true because our series converges for all x's. And it is evidently, this is a valid way to write sine x. Because when we test to see how close it is to sine x, we find it looks just like sine x everywhere. So that means it must be the right representation. Okay, here's what most people do with this stuff. Okay, listen. They become a nerd and they memorize this. Sine x is x to the odds, or odd factorial, times negative 1 to the n. Or alternating, and then it's like odd powers of x divided by the same factorial. Okay, so it contains x cubed over 3 factorial, and x to the 5th over 5 factorial, and x to the 7th over 7 factorial, and x to the 9th over 9 factorial. They memorize that pattern. It's not that hard to memorize. Then they throw in the plus minus, plus minus, plus minus. But where it comes from is the assumption that the nth coefficient is related to nth derivative at 0, and then this is just sort of a segue into something most people memorize, okay? So don't stress out if it's hard to understand. Just know that this means sine x. Okay, so how would you find a series for cos x?
Take the derivative.
You would follow the exact same rule here at the top of the page. This is your only relevant information up here. This, but starting with the assumption that f is the function called cosine. Okay? So let's give it a try real quick. Let's see here. Eraser. Eraser's not working. I need erasers. There it goes. I need to erase all this garbage. Not move it around. There it goes. Nice. Okay. How would you do cosine? It's exactly the same game. All right? So you would start with the assumption that cosine of x is cosine of 0 plus, what's the derivative of cosine?
Negative sign.
Negative sine. Negative sine of 0 over 1 factorial times x to the first plus, what's the derivative of negative sine?
Negative cosine.
Okay, so negative cosine 0 over 2 factorial x squared. What's the derivative of negative cosine?
Sine.
Yeah, positive sine. What's the derivative of sine?
Cosine.
Cosine. Like that. And you'll notice some of this stuff is just 0. In fact, every other term is just plain 0. So this is gone, this is gone, and you're just basically left with cosine x is, what's cos 0? 1, right? 1 minus 1 over 2 factorial x squared. So x squared over 2 factorial is your second term. Plus 1 over 4 factorial times x to the fourth. So in other words, x to the fourth over 4 factorial. Does anyone care to guess the next term without any calculus?
Minus x to the 6th over 6 factorial.
Okay, minus x to the 6th over 6 factorial. Good. Class, what's the term after that? Positive or negative?
Positive x to the 8th over 8 factorial.
Exactly. Okay, so there you have it. And then if you had to write it as a sigma, you can think of the first term as x to the 0 over 0 factorial, right? You could think of it that way. So if you're constructing your sigmas, it's kind of nice to have them all looking sort of the same. So it looks like you have an x to an even power, so that'd just be 2n. And on the bottom, you have the exact same number factorialized. And there's also an alternator. Okay, now, I actually already knew this answer without doing any calculus. And here's the reason. Sine x, if you take the derivative of sine x, you get cosine x, right? So if sine x was this power series, negative 1 to the n times x to the odds or odd factorials, when you take the derivative, you bring the 2n plus 1 down, and it reduces actually to this anyway. So if you take the derivative of this expression, it yields this anyway. But it's nice and comforting to see that this Maclaurin expansion recovers the same thing. Okay, now how many of you remember the old slogan that sine x is an odd function and cosine x is an even function? How many remember that? Maybe you remember it, maybe you don't. Remember, sine x has that beautiful origin symmetry, right? Passes right through the origin, it's got, you know, like that reflectional, double reflectional and rotational type symmetry. It looks really neat, right? Well, that shows up here in the fact that only odd powers exist in the power series. Look at that. X to the first, x to the third, x to the fifth, x to the seventh. That too would have a symmetry like that, origin symmetry, you know? So no wonder sine x is an odd function. And then cosine is an even function. See the nice y-axis symmetry? Well, that's also true for any polynomial with only even powers, you see. So 0th power, 2nd power, and so forth. So this preserves the parity of the function. Like it's still even after we analyze it a totally different way. Okay? Now we also saw the Maclaurin series for e to the x. Okay? So now there are three that you should sort of memorize. Okay, here they are. This is sine. Okay, this is sine. Don't forget the alternators. I sometimes get sloppy and forget my alternator, but that's very important. This is sine x. Then we have cosine x, which is really the same thing with just evens instead of odds. And then there's e to the x, which I worked out on the video if you want to see it. But it's actually the simplest of all of these. It's just x to the n over n. It doesn't have any odds or evens, no alternator. Everything's positive, it's beautiful. It's all positive. And it has every power of x, not just the odds or the evens. Okay? That's why it has no symmetry. Because it's both odd and even, I guess you could say, whatever. So, or neither odd nor even. These three you want to memorize, okay? And the cool thing about this three amigos set is they all converge for all x. So in other words, these are valid everywhere. Not just like -1 to 1 or 0 to 2 or some kind of weird little tight interval. These are all beautifully convergent for all x's. And that's very easy to prove using the ratio test. So let's say you wanted to find a power series for x e to the x. X e to the x. Is that a new one? Not really. You could just take x times the old one here. You already know the power series. We can do this again tomorrow. You already know the power series for e to the x, so you can actually just bring this into your sigma like this. I'll show you. Just multiply this in. And you get x to the n plus 1. All you're doing is distributing into a sum is all you're doing. So there's a new series right there. All right, you guys, I will continue that tomorrow. Tonight your homework is to work. Okay, so on this one, e to the 2x, you might think, oh no, I've got to find the first, second, third, fourth, fifth, sixth derivative. Then I've got to like plug in 0, and I'm going to get all the coefficients. No. Look, if e to the e to the x is simply this series, right? Then e to the 2x would just have a 2 here. It would just be a 2x instead of an x. In other words, e to the 2x has the exact same look as e to the x does. It just has a 2x instead of an x. It's basically the e to the x power series with a 2x inserted where the x was. That's not complicated, but you'll sure be glad you've memorized the power series for e to the x. Look how easy that problem was. Yes, question?
So for something like, would it be e to the, like, something x squared? Would that be x squared in the middle, or would it be different? So say if it was 2x
Yeah, that's a good question. I think what you're saying is, if we wanted to e to the x squared, could we just go, e looks like this. Let's throw an x squared in here. I think you can. Yeah, you can.
So you just put in any kind of
Yeah, it feels so illegal, you know, but it does. It feels weird to do that because you think, well, gosh, how could that possibly be so simple? But remember, this is a polynomial, right? It's just a long polynomial, and you can plug into it whatever you want. In fact, here's a cool thing you can do. Watch this. You can say that e to the first is just sigma n equals 0 to infinity 1 to the n over n factorial. In other words, e can be written like this. We saw another way of writing e earlier in the year. It's the limit as x goes to infinity 1 plus 1 over x to the x. E can be written lots of ways. It's interesting. This was a couple chapters ago. We talked about how e was actually the same thing as that thing. And now we're saying that e can be written like this. I mean, who knew that e is the same thing as 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial? Who knew? I mean, did you know that? Actually, I didn't. I didn't even think of that until just now. And then I think I saw it yesterday in a book, come to think of it. I just didn't connect the dots. You know, like I didn't know I'd explain this today, but when you asked me if it's okay to put it in x squared, I realized, oh yeah, I could show them. You could actually find e this way. You didn't have a scientific calculator, you needed to know e. try 1 plus 1 plus 0.5 plus 1/6 plus 1/24. That's a pretty good approximation of E. Pretty neat. Okay. You can also use power series to your advantage solving integrals, believe it or not. This is an ugly problem. You might have heard me mention it before. You've studied this function before. You know its limit at 0. You know its limit at infinity. But we've never been able to antidifferentiate it until now. Watch this. I want to find the antiderivative. Well, how about put in the power series for sine? Don't forget the alternator. I tend to forget alternators. I don't know why. You might say, Mr. Sure, you just made a big mess of my life. Why'd you put that in there? Well, think of it this way. Dividing by x is the same thing as multiplying by 1 over x. Right? So you might think I made things more complicated, but actually I made things more simple. Because look, now this 1 over x can distribute into the long sum of terms. All it does is just diminish the x to the 2n plus 1. This is x to the 2n times x to the first, you know. One of these x's is going to cancel with that x, that 1 over x there, see? So I'm just saying that this x cancels with one of these. That's it. All right, we're not quite done yet, but look at this. This is just x to the 2n now. You might say, I can't integrate this. Well, if you wrote out the first few terms, you wouldn't have any problem at all. In fact, we know how to integrate a series. We said before, all you do is just increase one power. Divide by the new power. It's like, how do you integrate x squared? Change x squared to x cubed, put a 300, right? Well, here we're going to take x to the 2n. We're integrating, so we're going to increase it by a power. Now it's x to the 2n plus 1. And then we divide by the new power. A little awkward. We got a 2n plus 1 and a 2n plus 1 factorial on the bottom. But we just integrated, so we don't need the integral bar anymore. Yeah, sorry. So we're actually done. So next time someone asks you to integrate sine x over x, instead of saying, I don't know how, you could say, well, I can write a series for sine x, and then I can integrate the series. You could do that. They'll like you if you do that. Here's what happens. If you plug in 0, you actually get just x from doing this. If you plug in 1, it goes negative, and you get x cubed over 3 times 3 factorial. If you plug in 2, it goes positive, and it becomes x to the 5th over 5 times 5 factorial. If you plug in 3, it becomes negative, and it's x to the 7th over 7 times 7 factorial. So if someone says, hey, integrate sine x over x, you'll say, I can't really, but I could give you as many terms as you want. What do you want, first 12 terms? Okay, write them out. It's actually pretty accurate. And if you wanted to integrate, let's say, between 9 and 10, or something, let's say it's a definite integral, you just plug in 10, plug in 9, and subtract. You'll have to pick, like, the first 10 terms. You can't do this for an infinite number of terms. But you can pick, like, the first 10 terms, right? Plug in 10, plug in 9, subtract. So this function, even though it's not really, like, a familiar function to us, it doesn't have, like, you know, the familiarity of sine and cosine and e and all that. This actually has a name, and this is called psi x. Psi x is the antiderivative of sine x over x. I like it. Pretty cool. We can solve problems we never could before with series, I guess. All right. I want to show you one more thing before we leave this page. Another thing you knew about sine x over x from a long time ago was that the limit was 1. Okay, this is not in my lesson, but it seems appropriate to mention it now. You guys have known for a long time that this is 1. In pre-calc, you were just told it was 1. You were told to believe it. You didn't really have any reason to believe it, except maybe you saw the pretty picture of the graph going like this. And you were said, look, you were told, hey, look, the graph goes to 1, so the limit's 1. It's like, okay, why? I mean, if I plug a 0, I guess sine 0 over 0, right? And then you learn L'Hopital's rule. And L'Hopital's rule shows us why it's 1, if you trust L'Hopital's rule. We didn't actually prove it in this class. But let me show you another way to see that this is clearly 1. You see, sine x is really just replaceable with this. X minus 1 over 3 factorial x cubed plus x to the 5 factorial, over 5 factorial, I mean, minus x to the 7th over 7 factorial, etc. What happens when you divide this by x? What happens? I'm going to go to 0, not infinity, sorry. What happens when you divide by x? Doesn't it simplify? It becomes 1 minus x squared over 3 factorial, right? Plus x to the 4th over 5 factorial, minus x to the 6th over 6 factorial. You've lost an x, but look at finding the limit. What happens when you plug in 0 for all the x's? Bam, bam, bam. What happens? You get a 1. Interesting. It's interesting. This is a totally different perspective from what you were taught before, L'Hopital's rule or whatever. I'm saying that sine x is the same as that garbage. Dividing by x gives us a 1 in the first spot. The others have x's, so when you find the limit, they all go to 0, and you get 1 in this way too. So interesting that we can approach the same problem from like so many different levels. A student who never took BC would never know that particular reason why limit as x goes to 0 of sine x over x is 1. Okay. You'll notice, though, that when we did our series so far, we've been finding, I was telling you that a series can replace a function, but it works like this. F of 0 plus f prime at 0 times x plus f double prime at 0 over 2 factorial x squared plus f triple prime at 0 over 3 factorial x cubed, etc. Right? That's what I told you. Why are we plugging in 0? Part of it was out of necessity, okay? But what would happen if we plugged in a different number? Okay, instead of 0 into the derivatives. Let's see what would happen. That's what we're going to look at here. First, let's talk about what happens when we plug in 0. Every time we have done this, it has caused us to end up with a series that represents the function, but the series is sort of built around the point x equals 0. Okay? For example, watch how cosine x is approximated when we use a result from the warm-up at the beginning of the lesson. You saw that cosine x is the same thing as 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Right? If you graph just the first term right here, cosine x equals 1, it looks like this. Does that look anything like the black curve? No. Well, maybe if you're near 0, right? If you're really close to 0, actually they do look quite similar. Okay? Let's use the first two terms. What does 1 minus 1/2 x squared look like? Well, 1 minus 1/2 x squared looks like this blue curve. So this is y equals 1. This is y equals 1 minus x squared over 2 factorial. That looks a little bit more like the cosine wave, right? If you use the first four terms, you can see the interval of convergence seems to be growing a bit. So I'm going to do green for this next one. But basically, it's going to look something like this now. An even tighter fit. And this is with 3 terms. So as we increase the number of terms, we get more and more of the cos wave. The curves hug the cos wave better. But you'll notice something. All of these have something in common. The center is at 0. See that? That's what I'm trying to say here. As you sketch out the first few partial sums, what value of x seems to be the center of each polynomial? Obviously what? 0, right? So x equals 0 seems to be the spot we are really approximating around, or building our power series from. So when I was in college, the professor would always say, the center of convergence is 0. I have no idea what he's talking about. What are you talking about? He's just basically saying that as you begin to make these curves, everything seems kind of centered at 0. Okay? And all of these are called Maclaurin series, anytime you're centered at 0. So far, everything I've done for you has been centered at 0 in this lesson. Okay? So let's look down here a little bit. As you can imagine, some series are troublesome at 0. They don't even allow us to evaluate anything. For example, look at ln, right? ln is not even defined at x equals 0. So let's say you wanted to build a set of polynomials that model the ln x curve. Good luck doing that at 0, right? This is ln. You cannot build any polynomials at 0 that match the graph. I don't know how you guys can learn this or pass the AP test if you don't pay attention. I'm serious. Okay? You're not going to be able to build anything at 0. There's an asymptote there. So we just can't build here. There is no Maclaurin series for ln. In other words, there is no power series at 0. There's no such thing. Okay? So you cannot build a power series representation of ln x from x equals 0 as a starting point. It's impossible. In other words, ln x has no Maclaurin series, is another way of saying that. Okay? So what are you going to do? You're just going to have to build it somewhere else. It's like if I said, hey, guys, we're going to build a rec room where we can put like foosball tables and soda machines and stuff. Well, you can't build that on a black hole. You can't build that if there's a big hole in the ground, you know. There's all sorts of places you can't build. You're just going to have to build somewhere else. So we can certainly model this with polynomials, but not at 0 we can't. In other words, there's no Maclaurin series. All right? So what we're going to do for ln is we're going to build it at 1. The graph is nicely defined at 1. Okay, so we're going to take an old rule, this idea here, and we're going to have to shift everything to the right. So we're going to shift to the right 1 unit. What's going to happen? Well, instead of the nth derivative at 0, it'll have to be the nth derivative at 1. Okay, so you're just going to have to evaluate all your derivatives at 1 instead of 0. You don't have a choice. Instead of x to the n, it's going to be x minus 1 to the n. So 2 changes happened here when we shifted to the right a space. First of all of our derivatives have to be evaluated at 1, or something besides 0. And all of the x's are shifted to the right one, so it's now called x minus 1 to the n. Because there's nothing at 0 for ln graph. No points to build upon. Okay, so now we can go ahead and find a series expansion for ln x. We'll have to do this at 1, but it's going to look like this. Instead of f of 0, it's going to read f of 1. Instead of f prime of 0x, it's going to be f prime at 1 times x minus 1. Instead of f double prime of 0 over 2 factorial x squared, it's going to read like this, f double prime at 1 over 2 factorial x minus 1 squared. Instead of f triple prime of 0 over 3 factorial x cubed, it's f triple prime at 1 over 3 factorial x minus 1 cubed. And the next term would be the fourth derivative at 1 over 4 factorial times x minus 1 cubed, and this goes on forever.
What would be before?
The fourth root, you can use IV.
No. You put x minus 1 to the
Excuse me, I can't count to 4. I'm going to have to go back to school and learn to count to 4. Okay, now, we need derivatives. First thing I need actually is ln1. Then I need the derivative of ln at 1. Okay, so I'll show my work nice and tidy for you guys, okay? So first thing I want to find is f of 1. That's just ln of 1, which is what, class? 0, right. Then I need to find f prime at 1, which means I'm going to take 1 over x. Where'd I get that? That's the derivative. I'm going to plug in 1. What am I going to get? Okay. Then I'm going to take the second derivative at 1. Now it's negative 1 over x squared, and I'm plugging in 1. And this gives me negative 1. Next derivative is negative 2 over x cubed, but I'm plugging in 1. Negative 2. And I think we should go at least to 4 or 5 derivatives to really see the pattern. The next one is negative, that's actually positive 6 over x to the 4th. And you're plugging in 1. So this is 6. If you take the derivative again, it's going to be negative 24 over x to the 5th. But you're plugging in 1. So it's negative 24. So your coefficients go like this. 0, 1, negative 1. Negative 2, 6, negative 24. It is a pattern. It's 0 factorial, 1 factorial. No, sorry, it's the first term doesn't count, but it goes 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, and it alternates. There's definitely a pattern there. Now, whether you can see the pattern or not, typically it doesn't matter on the AP test because we're not supposed to be like number experts. That's not the point of the test. What you would want to write is ln x is the same as the series 0 plus 1 x to the minus 1 minus 1 x minus 1 squared over 2 factorial. And then there's a minus, the next term is a minus 2. I'm actually on the x squared, x minus 1 squared term. Let me make sure I copied this right. Yeah. The next one is negative 2, and it's over 3 factorial. And this is x minus 1 cubed. And then the fourth term has a 6 on top, and there's a 4 factorial here. And then this is x minus 1 to the 4th. So they'll probably just ask you, okay, go ahead and build the first like 6 terms or whatever of the series. ln x at 1. Questions?
You said it alternates, but it goes from negative 1 to negative.
Yeah, it's not truly alternating, you're right. I think if you actually put it into a format, these are like factorials, and so like that's 2 factorial and it's over 3 factorial. So this actually reduces to 1/3. And this is 3 factorial over 4 factorial, so this reduces to 1/4. And then it doesn't alternate every term, but it has like a negative 1 to the n squared plus 1 over 2. It's like this plus plus minus minus kind of thing. Anyway, the point is, on the AP test, they'll ask you to write out the first few terms, not to create like a series, you know what I mean? Like a sigma. So if you don't have to create the sigma, you don't have to see the pattern that well. Okay, so tomorrow I'm going to give you a handout that has the Maclaurin series for cosine, Maclaurin series for sine, Maclaurin series for the e to the x. It's got the, not the Maclaurin series, but the series expansion at 1 for ln, so this will be on there. These are very famous ones, right? Very famous ones. Granddaddy Macho's on there. Basically all the series we've done are all summarized. And they're called the known Maclaurin series, like we know them. Except this one's not Maclaurin because it's not a 0. Okay, so we built at 1. Could we build somewhere else? Like, just now we created a polynomial, guys, that look like this. Basically, our polynomial looks something like this. The one we just wrote out looks like that. It hugs the curve pretty close. The more terms you add, the more hugging it does. could we have done this over at like x equals 3 or something? We could. What we would do is this would be a 3 and x minus 3, see? So what you need to understand is that Taylor actually came before Maclaurin, and Taylor said this. Taylor basically got this rule written down. I'm sorry, this is Maclaurin's rule. This is Maclaurin's rule, and he was Scottish, not English. I said it wrong the other day. But Taylor had a more general version of this, and it looks like this. Instead of always evaluating your derivative at 0, you can actually evaluate it wherever you want, as long as the function is shifted to the right by that much. So this is the better of the two to memorize. The second one in blue, it's more general. It's true for all valid A's. You know, this is Taylor's version of it. And Taylor's version actually came first. Maclaurin got a lot of credit for a lot of nothing. Okay? What he did was, the Scottish guy, he's like, oh, Taylor's there, very cool. I'm going to make A0. So he made A0, and he got all the credit for that. They call it Maclaurin Series. All it is a Taylor series with 0 plugged in for A. So it's kind of a weird historical mishap there, but this happens a lot. Why is it important to have Taylor's formula? Well, not every function can you plug in 0. We saw that with ln, right? Also, not all series, remember I told you that sine x, right, is wavy, 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 right? And if you put like 12 terms together and you form a polynomial, you get like, ooh, this really nice tight fit, you know? It's a polynomial, it's not actually the sine wave, but the first 12 terms of the Maclaurin series does a good job of approximating sine x, right? And the more terms you add in, the more the blue covers the black. In fact, sine e to the x and cos x, if you let it go all the way to infinity and you include all the terms, you get the whole curve. That isn't true on the previous page. On that previous page, when we drew this picture of ln x, and we built our little power series at 1, unfortunately, no matter how many terms you do, no matter how many, you could do 1,000 terms, but everything falls out of convergence at x equals 2. You could do 1,000 terms, but the best you get is 0 to 2. You can't get the whole ln graph modeled by a power series. It's impossible. You can't get it all at once. You only get like 2 spaces at a time. So let's say you wanted to build at 1, you only get 0 to 2 convergence. See? So if you wanted to study like the polynomials out at ln of 14, you would want to build your Taylor series out at 14, use A14. And that would give you basically between 13 and 15 polynomials that model ln in that region. Okay? So I'll draw what I just said. Let's say you're out here at 13, right? And you do an A equals 13 Taylor series. You're going to basically get a nice match between 12 and 14. That's it. That's all you get, no matter how many terms you include. So this is why Taylor's theorem is so important. Not all functions have a 0, you know, x equals 0, and not all functions, not all power series, can model the curve perfectly. So you're just going to have to, if you want to work at 13, you're just going to have to settle with a shifted power series at 13, and it's going to have to just suffice that you're studying 12 to 14. If you need to study 20, don't run the power series. Okay? So this thing is called the Taylor series right here, and it's also called Taylor's theorem right here. All right? Okay, so tomorrow you will get a list of Taylor series and Maclaurin series that you should memorize, and also what intervals that they're valid on. Okay? Okay, let's say that you have a power series like this. I just make up this power series. Let's say it's x over 2 to the n over n squared or something. How would you know like what Maclaurin series that was? Is that sine? No, it doesn't quite look right. Is it cosine? No. Is it e? No, not really. What is it? Well, not sure actually, but I can tell you one thing. For certain numbers x, this doesn't converge anyway. For example, if x was, let's say 3, this is top heavy. It's a geometric on top. It's a divergent geometric on top alone. So this doesn't even converge, you see. On the other hand, if x was 0, this is just the series 0 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0, and that converges. But if x is 1, maybe it would converge, you see. So what we typically do on this is we study this and say, what x's does it converge for? And if you want to find what x's it converges for, you just use a ratio test, like this. So you just do LIM n goes to infinity, right? You basically take the n plus first term divided by the nth term. You force it to be less than 1, and you solve for x. We've done this before. You just take the n plus first term divided by the nth term. Where'd it go? It was there a second ago. Oh, there it is. And you set it less than 0, because this is ratio test is less than 1. That means converge. And then usually this simplifies quite a bit. We've done a few examples of this already, warm up and stuff. But basically, all the x over 2 to the n's cancel out, and you're just left with an x over 2 on top. Then you're going to have an n squared on top, and you're going to have an n plus 1 squared on the bottom. You can even pull out the absolute value x over 2. And then you ask yourself, when is this true? Well, what is the limit of n squared over n squared plus 2n plus 1? What's this limit? It's 1, right? That limit is 1. So now this problem looks like, yeah, this is n goes to infinity, thank you. This is just x over 2 times 1 is less than 1, which is another way of saying x over 2 is between negative 1 and 1. Okay, so x is between negative 2 and positive 2. So we've actually done this before. I'm repeating myself. I did this 2 days ago. I did it 3 days ago. We did it as a warm-up. This is called finding the interval of convergence. You should have done it a couple times, maybe. I'm not sure it's been on any worksheets yet, but it'll be on my next one. But there's interval of convergence. What this means is if you construct a power series for that awkward series, right? Or if you look at it, it only matches its curve between negative 2 and 2. Unfortunately. Like it's not a perfect match for the whole curve. It's just that little four-space window there. And we often will say now that the radius of convergence is 2. What that means is f is some crazy function, right? The power series matches well. If you use lots of terms, you know, the power series matches well, but only on this interval, this little window. And if you look at half of that window, that's called the radius of convergence. So the radius of convergence is 2, you could say. Or you could say the interval is negative 2 to 2. So if you state half the interval, you're stating the radius of convergence. So. Okay. And then will it converge at the endpoints or not? We've talked about how we'll just wait on that question. We're still going to wait on that. Sometimes these are both less than, sometimes they're less than equal to, sometimes one of them is less than or equal to, the other is less than. Okay? But that's how we decide. You just set up a ratio test, force convergence. So we'll just test on a case-by-case basis for that. Okay, and then tomorrow I'll talk to you about how to create a Taylor polynomial. And a Taylor polynomial is just basically a polynomial that models a portion of a function. It's kind of like tangent line approximations, only it's a polynomial approximation of a curve. Okay, so we're going to pick it up from right here tomorrow.